Hello, guys. We'll be presenting in about 10 minutes. You can mark your attendance here. This form will be open for about 15 minutes. All right, guys, I'll be starting now. If any of you have not filled this attendance form, you can fill it. It'll be open for the next 5 minutes. Yeah, so let's start talking about recurrences. So this session will be mainly on recurrences and differential equations. Yeah, so I'll be covering recurrences. I'm Prajit, and my friend Anirudh will be covering differential equations, which is in the second part of the session. Yeah. Okay. So recurrence is uh, a a sequence is basically an ordered list of numbers where each term will have a position. So if we consider the sequence 2 comma 4 comma 6, so 6 will be the third term, so we represent it as a3. So a3 is the sixth term, so an will give the actual value of the term at the nth position. So that is a sequence. A general sequence will be of a closed form where we can directly evaluate the nth term by using the value n. So here we can evaluate the third term by using n, which is just 2 times 3. So that's 6. But in a recurrence relation, however, we cannot do this. In recurrence relation, we will have the nth term to be a function of any or all of the previous terms, including n. So to find the nth term, we will need to repeatedly compute all the previous terms. So like here, as you can see here, the nth term will be a function of all the previous terms and n. So let's consider an example here. So consider this staircase example. So what happens is what happens is the staircase has n steps and we might climb one or two or three steps at a time. So we cannot take a 4-step jump, but we can step up 3 times or 2 times or once. So if we want to reach the nth step, we can either do that from n minus 1th step or n minus 2 or n minus 3. So there's only three ways to reach nth step. There's literally no other way of reaching that. So if you're in n minus 4th step, you will need to come to n minus 3 and then you can hop on to n. So if we represent an to be the number of ways of reaching the nth step, we can write that as the number of ways of reaching n minus 1, and then we can add to n minus 2 and n minus 3, because there's no other way of reaching our step over here. So this is called a recurrence because there is no direct way of computing what the an value will be. It cannot be written as a function of n. You cannot write this. So yeah, but we can actually solve this recurrence and then write it in this form, which is what we'll be covering in this whole lecture. Okay, let's consider another example. So this is the rabbit riddle. It's a very famous riddle. So a farmer will place two newborn rabbits in a field. So the newborn rabbits will mature once in every month, and the rabbits never die. So the question is, how many rabbit pairs will be there after n months? The mature pairs will always produce one new pair every month. So let's model this one. So in the first one, there'll be one pair, which is the initial pair kept by the farmer. So we will have that one pair. Yeah. So I'll circle the pair if it matures. So in the second month, this pair will mature. So we can circle it. So now it has not reproduced yet. So in the third month, this pair will reproduce. So this pair remains and it'll have an offspring. So there'll be two pairs in in the end of month three. Then in the next month, this original pair will remain as is and it'll reproduce once again. So because in every month the same pair will always reproduce. So there'll be one more offspring. Now this pair would have matured. So there'll be this pair would have matured. So I'm circling that. So there'll be three pairs in the end of month four. And then in the end of month five, what happens is this matured pair will give an offspring. So there'll be two. Next, this pair will mature now. So that'll be that. And then this matured pair will again reproduce. So that'll be that. So we will have five over here, and this will continue so on. So we can model the population at this month to be all the rabbits alive in the last month. So we will have, for example, if we want to find the number of rabbits in the fifth month, it would be the rabbits in the fourth month plus the number of newborn rabbits for this month, which will be exactly equal to the number of rabbits in the previous month. Because the birds only come from rabbits which are already mature. So the rabbits which are already mature happens 1 month earlier. So we will have to add the previous 2 months to get our third month. So we can write this as this recurrence. There is no way of directly telling what is the number of rabbits in this month. However, we can solve this recurrence and then find the number of rabbits in any month M, which we will see in this lecture. Is there any doubts? You can always put your doubts in the chat. I'll have a look at it. Yeah, this sequence is called the Fibonacci sequence. We'll learn to solve it. Okay, now let's go on to the classification of recurrences. So recurrences, there are mainly two types of recurrences. There is linear and there's non-linear. So a linear form, there'll be a general representation of linear form is like this. In a non-linear recurrence, it will be a function of all the terms, but it will have non-linear terms like multiplication, square, trigonometry, exponential, logarithm, etc. We'll not go into depth in non-linear because solving them is not that easy. But in linear recurrences, there are standard methods of solving them. So let's consider this standard linear recurrence. So I will talk about three terminologies. So these are important for classifying. Only if we classify, we'll be able to solve the recurrence. So if we set the coefficients to be functions of n, so there is an minus 1 till an minus r. And my an minus r is the n minus rth term of the sequence, and nth term of the sequence is a. So if we set the RHS, which is g of n, to be 0, then it is called a homogeneous recurrence. And if it is not 0, it is non-homogeneous. In general, it's much easier to solve homogeneous recurrences compared to the non-homogeneous ones. If we set all the coefficient functions f of n over here to be equal, then it will be a recurrence with constant coefficients, which are also much easier to handle compared to a general recurrence, which is in terms of n. If the first term and the last term over here is not 0, so if an and an minus r exist in this recurrence, we can say the order is r. So order will be the difference between the maximum difference between the terms. So if we have n and n minus r, so the difference between them is r. So that will be defined as the order of the recurrence. So these three are very important. So we'll have some examples. Yeah. So okay, so these are the examples now. Let's consider the first one. Yeah. So first one is an plus 3an minus 1. So this is directly we can see it's a linear one because there is no non-linear terms like multiplication, product, etc. And it is a homogeneous because all the RHS is going to be 0. The coefficients of all the terms are constant here. So we can say it is a constant coefficient recurrence. So consider another example here. So this is very similar to this one, except the coefficient is n. So it'll have a variable coefficient. So there's a third example. Now this example is similar to this one, but there is a 1 in the RHS, if you can see. So because of this 1, it becomes non-homogeneous. In fourth example, we are not having a zero here, so again it is non-homogeneous, and it is having n here, so it's a variable coefficient. Yeah. Next, we'll go to non-linear ones. So these are non-linear because there is a product term here and product term here. So because of this product term, they become non-linear, and there is no sense of homogeneity for non-linear recurrences, so we don't talk about that. Yeah. Next, we are having second order ones. So these are second order recurrences. So second order recurrences is called so because again, the difference between the highest order and the lowest one is 2. So n minus of n minus 2 is 2. So that will be a second order. It is a linear recurrence. There's no nonlinear term. Now this one is homogeneous because there's a 0 in the RHS, and this one is non-homogeneous as there's a 5 over here. We'll learn to solve most of these.
Rajat, can you explain why the fifth example is a recurrence? Somebody's asking a doubt. It can be solved.
Yeah. So what happens is there are many recurrences which can be solved. There are very simple recurrences, as I'll show in the next few slides. But a recurrence is just defined. It's not like all recurrences not solvable. There are multiple classes of recurrences. Few are solvable. Many are not. Now the fifth one, this is clearly solvable one, but we will still classify it as a recurrence for now. There's always ways to solve them. Is there any other doubts? Okay, I'll move on. So here are a couple of problems for you all to try. You can put the answers in the chat. I'll wait for a little time. So consider the first example. So what is the order of this one? Guys, please put the answers in the chat. I'm viewing it. I'm not getting any answers. Okay, fine. Yeah. The first one is linear and non-homogeneous, and the order is not defined for the first one. Yes, it's correct. Because there is no clear way of writing n minus of the GIF or the fractional part, I mean, floor or this ceiling functions. So it is, the order is not defined. For second question, guys, answers for second question. Second question is not linear because we are having a product over here. Yeah, the steam delay, right? Yes, it is a homogeneous one with order 3, and it is non-linear. And homogeneity is not defined for non-linear ones. Okay, question 3. Okay, I'll move on. The question 3 order is 2. It is linear and it's non-homogeneous because of this one, but it is having constant coefficients. You can go through all the other examples as well. Here are the answers. Yeah, the last example is especially important. So what happens, you can actually solve this example. You can actually simplify this one. So if you write an plus an minus 1 whole square and simplify it, you will simply get an. I'll write it. You will simply get an plus an plus an minus 1 equal to 0. That's what you will get over here. So because an plus an minus 1 equal to 0 is the simplified recurrence of this one, it will be linear. It is no longer non-linear. Here it looks like there's a non-linear term, but one simplified will be linear. And it is a homogeneous one because, again, there's a 0 in the RHS and it's having constant coefficients, which is 1. And the order is also 1. It's not 2. Okay, next let's consider simple first order linear recurrence. So these are stuff you might have learned in classes 10. So there is arithmetic progression. So it's a very simple way of representing them is that difference of consecutive terms is constant t. Yeah. So when we repeatedly substitute, no, the next term which is an minus 1 is going to be an minus 2 plus d. Again, because just by substituting n as n minus 1, we will get this term. And then this will simplify to be this form. Now, again, we can substitute an minus 2. And we can do that so on and so forth. So what we'll get is that an is equal to an minus k plus k into t. So when we choose k to be n, we will get this term will be 0. So an will be a naught plus nd. So this will be the this will be the solution of this recurrence. So this is a very simple recurrence. You might have learned in class 10 or something, which is an is equal to a plus n minus 1 into d, which is very similar to this one. It's actually the same thing. The difference being that here we are starting from a naught term and here we are doing from a one term. That's the only difference. So that's why there's n minus 1 here. But effectively they are the same. Okay. Next, we'll talk about geometric progression. So geometric progression is where the consecutive terms differ by a product of r, where r is going to be a common ratio. So if we repeatedly substitute again over here, similar to this method, so an is going to be r into an minus 1. So if we substitute an minus 1 to be r into an minus 2, and again, ar, and this one again we can substitute back. So we will basically get this expression that an is r bar k into an minus k. So if we choose k to be n, we will get this term. You might have also learned this as in school. You might have learned that anth term is uh, a into r to the power n minus 1. Again, because a over here is going to be your first term, not the 0th term, as we have written here. Just a matter of convention. Any doubts to you? Okay, let's continue. Yeah. So now comes the real deal. So this is not something you might have learned. So these are some unique techniques which you can keep under your sleeves. So this is the first one. So this is a general first order linear non-homogeneous with constant coefficients. So if you see this clearly, this is non-homogeneous because it's a constancy here. And it is linear and it is having constant coefficients. So to solve this, there's a unique method of substituting. We'll consider another sequence, Bn. So Bn will differ from An by lambda. So lambda is a constant that we are assuming, whose value we will compute soon. So the value of this lambda we will compute soon over here. But by substituting this, we'll have a unique leverage. If we substitute this back here, we'll have bn plus lambda equal to c1 into, yeah. So also what happens is an minus 1 will be equal to bn minus 1 plus lambda. Just by replacing n with n minus 1, an minus 1 will be again bn minus 1 plus lambda. So by substituting this back in an, we'll get this equation. Now what happens is, if you simplify this, we'll have this expression. This part of this expression is completely constant if you observe carefully. Now you cannot really control the value of C2, so that will be given in the question. But you can control the value of this one, because what happens is, if we ensure that this goes to zero, if we ensure that this term goes to zero, we will have a simple geometric progression, that bn equal to c1 into bn minus 1, and you all know how to solve a geometric progression. So if we substitute this part of it to be zero, we can simply solve for lambda. It will be minus c2 by c1 minus 1, which is this one. So this is what we consider lambda to be. So if we ensure lambda is this one, then we'll simplify the sequence to be this one, which is very easily solvable by GP. So if we consider the first term to be first term to be b1, and the common ratio will be c1 here. So by solving, you will get this. Yes. So once you solve for bn, we can simply substitute back again. So an will be bn plus lambda. So an will be bn plus lambda. Yeah, what is b1? So b1 will be equal to alpha minus lambda, because alpha is basically the first term of the sequence given, which is, it'll generally be given in the question. So alpha is equal to a1. Write it here. Alpha is equal to a1. So once you have alpha is a1, so b1 will be simply alpha minus lambda, a1 minus lambda. So we substitute b1 here and we can solve for it. Next, we'll consider first order linear homogeneous. So this is not non-homogeneous. Non-homogeneous is a very general case. We'll consider that next slide. This is a this is a homogeneous one. So this is very similar to GP, except the coefficient is not constant here. Coefficient is f of n here. Yeah. So what happens is, we can take the ratio of nth and n minus 1 term here like this. This is the solving our strategy. So we can take the continuous product from 2 to n of this expression. So if we take n minus 1 over here, if we put f of n to be f of n minus 1 here, we will get f of n minus 1 to be equal to a n minus 1 by a n minus 2. Simply by substituting n to be n minus 1. So if we do this, we will get consecutive terms, and we are multiplying all this to 2. So what happens is, we can see that these terms cancel. This is called telescopic effect. So we'll cancel all these terms and we'll end up with an by a1. So we will have that an is equal to this expression. An is equal to the RHS multiplied by a1, and a1 is alpha. So we'll put that in and we'll solve it. Now f of n is generally given in the question, so you can compute the value of the nth term always. I'll wait for any questions. Yeah, someone has asked how we'll replace lambda. So lambda, that's the whole point of this method. By substituting bn plus lambda, we can enforce that this part of it is zero. We are forcing it to be zero. By ensuring it is zero, we'll get a GP, which is easier to solve. So by forcing this to be zero, we can solve for lambda. C1 and C2 are things given in the problem. mean, this is a unique strategy. Like, this is what you are supposed to learn in the session, because it's not very easy to think of how to solve this. There's no direct way of solving it. That's why this unique substitution. Yeah, okay, I'll continue. Okay, so this is the next example. This one is first order linear recurrence. This is a general, most general example. So here there is not this, it's non-homogeneous, and does not even have a constant coefficient. How is the product fn into fn minus 1 computed? So this is given in the question. So f of n is I have written it in a general format over here. So in the question, for example, f of n might be n cube or n square plus n. So we will know the exact expression. So we can compute it in every instant of time. There is stream delay actually. Let's look into that. Yeah. So let's consider this example. So so the strategy to solve this one is also very unique. So when we see this example, so we can see a coefficient of n and n minus 1 into n factorial. So we'll let this part to be f of n and this part to be g of n. Now alpha is the first term. So first term is 1, it's given. Now Pn, I'm defining the thing called Pn. So Pn is, I'm taking it product from f of 1 to f of n. Why, you may ask? So this is a very unique strategy. This is also a way to solve this. I'll go through the actual template of solving any general question in the next slide. But this is an example. So f of n is n. So if we compute these for every term, so f of 1 will be 1, f of 2 is again 2, f of n is n. So when you multiply the product from 1 to n, it is n factorial. That is the product Pn. It is something I have defined on my own. Now what I'm going to do is I'm going to divide this whole recurrence by n factorial. Now n factorial is simply Pn. So I'm dividing the whole thing by Pn. Why are we doing this? Because by ensuring we are dividing by n factorial, the a nth term will be divided by n factorial. Yes. The a n minus 1th term will be divided by n minus 1 factorial, because there's a term of n in the numerator that will cancel with n in the denominator. We will have a n minus 1 factorial in the denominator. So we will have this term. And now we are dividing by n factorial, so this will cancel with this, and we'll end up with this. So if you observe carefully, we can set this substitution. So this is exactly why we have done this method. By doing this method, we can ensure to substitute an by n factorial as vn and an minus 1 by n minus 1 factorial to be vn minus 1. So we get this term. Now we can simply plug in values. So again, now once you got this expression, the next step should be obvious. So we will write consecutive terms and cancel them. So if I write vn minus vn minus 1, so this will be n minus 1. Next is vn minus 1 minus vn minus 2. So that will be n minus 2, and so on. So if we see this, we can cancel these terms. If we add all these, we add all of this to right to the my bad, right. Yeah. So if we cancel all these terms, we will end up with the first term and the last term. So the first term is Vn and the last term will be V1 over here. And if you see carefully, RHS, if you see, it will be the sum of 1 plus 2 plus 3 dot 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 till n minus 1. That will be your RHS because you're adding all that. So if we solve this, we will simply get n minus 1 into n by 2. So this will be your solution. Now V1 is simply, Okay, so V1 is simply the first term, which is A1 by 1 factorial. So that A1 is given to us is 1. So we'll simply put that in, we'll get 1. And so V1 we can know, and Vn is again An by n factorial. So we'll just solve that, you'll get the answer. So you see, it was not directly obvious to make this division. So that's why we must have some intuition to do this. So I have written the same exact method in a more general format in the slide. So I've just considered general functions f of n, g of n. So if we divide by the product from f of 1 to f of n, the whole expression, which is called Pn, if we make this division, f of n will get cancelled. We make this division, f of 1, f of n term, if you divide here, it will get cancelled. And you will simply end up with this term and this term. So again, we'll substitute Vn, we'll get this, and then we'll do the telescopic method of adding all the terms. We'll get the first and the last terms. And you will simplify that by substituting Vn to be An by Pn, V1 to be A1 by P1. You will solve that and you will get this. G of R is again a general function which will be given in the question. Any questions or doubts? Yeah, so someone is asking what if there is a zero term? So there can be a zero term. It is if there is a zero term, we can I'll write it once. So the what last term which I had taken was V2 minus V1 is equal to something. So we can also write V1 minus V0. And then if we add it, these terms will all get cancelled. So we will simply get V1 instead of, we will simply get V0 instead of this one. One sec. Yeah, so simply we'll get V0. And this one will simply have a first term over here. Instead of 2, it will be a 1. No, n is greater or equal to 2 is not necessary. I mean, in this, it depends on the question. They might have given the question. So in this question, it is given n is greater or equal to 2. So it is enforced, but we might have a question where n is greater or equal to 0 also. It's fine. Let's continue. Okay, so that was it for the first order linear recurrences. So that will cover all the types of first order, homogeneity, non-homogeneity, constants, all of it is covered. So next, let's go to second order ones. So yeah, so this is the second order recurrence. Yeah, so this is a general second order recurrence. So this is second order because the difference between n and n minus 2 is 2. So that is second order. And it is having constant coefficients. P and Q are going to be constants. Now, so a general strategy over here is to substitute x to the power n over here for an. So you might have observed in general recurrences, the solution is of the power of the form x power n. So, so to solve this one, there's no direct way of solving it. So we do the way of called characteristic equation. So characteristic equation is when we substitute an to be x power n. So I just substitute an to power x power n. An minus 1 will be x power n minus 1. An minus 2 is x power n minus 2. So x power n minus 2 we can take common and cancel out. So we'll get this expression. So this is called a characteristic equation. This is called a characteristic equation. So, and this equation will have two solutions because it's a quadratic. We'll have alpha and beta. So there are two possibilities. First case is when alpha is not beta, and second case is alpha is beta. So if alpha is not beta, they're both distinct solutions. Then we can write the general solution of this format. So lambda or mu are going to be constants. They're going to be constants. Alpha and beta are the roots. So this is basically superposition of the two roots, alpha and beta. If you substitute this back over here, it'll always satisfy for every lambda and mu values. It'll satisfy. You can always check it out by substituting. You will need to use some results like alpha plus beta is p, and alpha beta is going to be minus q. Some stuff which you might have learned in 10th. And if alpha is beta, then we cannot simply substitute alpha is beta here and write 2 lambda alpha power n or something. This does not work. We will have this sort of form. So nth term will be lambda plus mu n into alpha power n. This recurrence is very important because Fibonacci and even the first 2, 3 recurrences I had shown you in examples of this form only. No, we are not substituting an to be xn. It's not equal to x bar n. It is just a method of solving. So someone has in the chat has asked if we substitute an to be equal to x bar n. We are not substituting equal to. It is just a way of getting the characteristic equation. An is in fact not equal to x bar n. If you solve it, you will get an is this one. It's not, there's no x here. So x is just a way of getting your characteristic equation. So yeah, without characteristic equation, you cannot solve it. So we need a characteristic equation. That's how we put a general solution of x bar n format. So in a linear recurrence, you will have x bar n format as solution. So we'll simply it's just a guess. So it's a guess, and we'll put that guess back into the equation, solve it, and you'll get the root. Yeah, it is a form of guess. So yeah. Next, let's go to non-homogeneous, which is of this format. So it's basically this expression with the constant. Uh, yeah. So K is contributing to the non-homogeneity. So if we substitute K, if we what we do here is again we make the substitution. So in general, for non-homogeneous method questions, this substitution works. So if we make the substitution here, Bn is another sequence. If you make the substitution here, we can simplify that and you will get this. You will get this expression. See again, there is no proper derivation to get this one. This is a characteristic equation, and from that we are getting this. So if we, what happens is if you put 2 lambda into alpha bar n over here, it will not satisfy it. We need an nth term, only then we will get alpha bar n terms in the equation. You can try it, you can substitute and check it. Okay, and over here, you will get this expression by substituting this. Again, so we will enforce the RHS to be 0. So what happens is C is a constant that we are choosing. It could be any constant. So if I choose a C such that the RHS over here goes to 0, hello.
Rajan, I think people are still confused about why you're using X bar and like when and how it's not equal to like AN. I think it's better if you
Yeah,
explain
fine.
that once.
So what happens is x bar n is not an it's not an is not directly equal to x bar n. So x bar n is a way of uh, getting the solution. So what happens is we need a characteristic equation. So we need a root. We need some value to the power n to be the representation of the solution. So to get that value, we substitute x bar n. So x is something which we don't know and we want to find x. So we need a root to the power n to be the actual solution of this equation. So that's why we put x. So x is something which we don't know and we want to find it. So here is a question. So this is the Fibonacci, the famous Fibonacci series which we have seen in the starting. Yeah, so this is a standard Fibonacci series. So this is a solution of how you solve it. So instead of finding terms one by one, we can find directly the thousandth term or 2000th term. You can directly find it without finding all the previous terms. So again, we the standard method of replacing by x bar n. So x is something which we don't know, we want to find it. We will put that in and we will simplify it. We'll get this. So we'll get two roots. X is 1 plus or minus root 5 by 2. This is what you will get. So again, alpha and beta are not equal. So alpha is not equal to beta over here. So we will go to the first case. The first case here is where alpha and 2, two constant lambda and mu, alpha par n, beta par n. So one is alpha, one is beta. So we'll substitute that here. Yes. So once you substitute that here, you get this format solution. Lambda and mu are something which are unknown. So to find lambda and mu, we use the initial conditions given the question. So a1 is 1, a2 is 1. So we will substitute a1 to be 1. So what happens if you put 1 here, you get lambda into this power 1, this power 1. So you get one equation here. And the second equation here is where you put lambda into this power 2. So if you square this expression, you will get 3 plus root 5 by 2. To square this expression, you will get 3 minus root 5 by 2. You will substitute both back here. And now you are having two equations in two variables. So this is something you might have learned in 8th, 9th, 10th. So if when you're having a linear equation in two variables, you can substitute, you can solve this here and put that back here and solve it. Many ways to do it. So once you solve it, you will get lambda and mu values. So once you're having that, you can simply put those values back over here and you will get this. So this is a very complicated form. So again, solving it manually is not possible. You cannot find the thousandth term by putting it here. So in general, it's preferred to stay in the recurrence format. So that is the advantage of recurrence format. So when you're having a recurrence format, you can manually compute. You cannot manually compute the 30th power of this one, but you can manually solve it and find 30th. In computers, this is obviously the matter way.
For those of you who are asking why after getting alpha and beta, we get a general solution, that's because we're using the principle of superposition. And since there's no constant term in this recurrence, we are just, multiplying it by two constants, lambda and mu. And I think Prajit can explain this better.
Yeah. So in first order recurrences, the solution is of the form alpha par n. There's only one alpha. It'll be of the form alpha par n. But in second order, you'll need two numbers. So that's called again superposition. So we need two solutions alpha and beta, which we superpose together to get the final root. And yeah, here we are having 1 plus root 5 by 2, which is indeed your golden ratio. And golden ratio is again derived by this quadratic, which is also very deeply connected to Fibonacci sequence. You can search it up online. There are some, I think the consecutive, I think there was something, I'm not very sure, but one second. Yeah, something like an by an minus 1. If you compute this from limit n approaches infinity, as n approaches infinity, if you compute this, you will get the golden ratio or something. Again, this is also comes from the solution of recurrence. You can write out yourself. You can plug in nth term, n minus 1th term, and divide them and take limit n approaches infinity, and you will get golden ratio. Yeah. Okay, let's go to the next. So this is an extension of your previous second order linear constant coefficient. So this is nth order linear constant coefficient. So this is the general form of it. So we are having an minus 1 till an minus k. So it will be kth order. And these are coefficients. So again, we use the same method of superposition, and with x bar n, we want to find the roots. So again, if it is kth order, we'll need k roots, which is exactly why we will substitute x bar n back here. We'll simplify it. We'll cancel x bar n minus k as a constant factor. So we'll just put that in and we'll cancel it out and we'll get this equation. So this is called the characteristic equation of this recurrence. Okay. So this characteristic equation will have k roots. Case 1, if all these k roots are going to be distinct. So if all are distinct, again, it is exact same as your previous method. We will write constants multiplied by root power n. Constant multiplied by root power n and simply add it. Very simple. But if there are, so let's now talk about multiplicity, root multiplicity. So if not all roots are distinct, if there are a couple of roots which are repeated m times. So for example, if you're having an equation whose solutions are 1, 1, 1, 2, 2, 3, 3, 3. So then if you see this root 1 has a multiplicity of 3, 2 has a multiplicity of 2, 3 has a multiplicity of 3 again. So if you say the multiplicity of this root is 3, so that is what is mi. So consider that instead of k roots, k distinct roots, we are having only p distinct roots. So p is a value which is less than or equal to k, and there are only p distinct roots. So there are a couple of roots which is having a multiplicity more than one, because of which we will cover all k roots. So let alpha I, which is the ith root, let it have a multiplicity of mi. So if we are having a multiplicity of 1, it means it's appearing only once. If it's having 2, it's appearing twice. So in that way, we will get all the k roots. So multiple of them are equal. So this is a general solution of this. So it looks very complicated. Let me go through it slowly. So what if you see here carefully, we had one root. So we are having one distinct root with multiplicity of 2. So we had one constant here, and n power 1. So if you see carefully, this is a general polynomial of degree 1. So degree 1. Over here, we will have a general polynomial of degree, your multiplicity minus 1. So there we had a multiplicity of 2. Here we had a multiplicity of 2. Alpha and beta are both equal. So we had a polynomial of degree 1. So if we generalize that, if we're having multiplicity of mi, it will have a polynomial of mi minus 1. So that is dependent on the root. So there we had one root. So we had only one expression, one term. Here we are having a lot of roots. Yeah, the roots can also be complex. So we will have a complex recurrence. It's actually possible. Okay, so if you do that, so we are having all the distinct roots in powers of n, and inside we are having polynomials of order of degree mi minus 1, which is the multiplicity of your root. So whatever root you are having, its multiplicity minus 1 will be the degree of your polynomial. Let's go to an example, you'll get it. So this is the example. So this is recurrence of order 4, n and n minus 4. So your recurrence is of order 4. And these are the initial conditions. So first you will find your characteristic equation. Yeah, once you are having characteristic equation here, then you will simplify that, you get a biquadratic. So there are multiple ways of solving this. In general, in normal equations, you will be given a simple biquadratic whose solutions can be guessed. So you can guess 1, 2, minus 1. There are standard guesses. In general, there's a trick actually in polynomial equations. If the polynomial has integer coefficients and then it's, if it has any integer roots, then its roots will be plus or minus the factor of the constant, factor of your constant term, divided by the factor of your coefficient of the first term. I think it's called some integer root theorem, I'm not sure. So here if you see, it will be plus or minus factor of 2 by plus or minus factor of coefficient of this, which is 1. So you can, there'll be only 4 or 5 cases which you have to check. So if you check that out, you will find 1 and 2 have to be the only roots of this. So 1 and 2 are both, again, factors of 2 if you check it out. Yeah. So once you solve that, you will get this as solution. Now, if you see, observe carefully, 1 is having a multiplicity of 3. And 2 is having a multiplicity of 1 here. So 2 will have a polynomial of degree 1 minus 1, which is the multiplicity minus 1. So multiplicity is 1, so the degree will be 0. So a general polynomial of degree 0 is just a constant. And this one is a polynomial. 1 is appearing 3 times, so you will have a general polynomial of degree 2 inside. So that is that. It's a quadratic. So now you're having 4 constants in your recurrence and you're having 4 initial conditions. So you will simply solve the 4 linear equations you will get here. So you will put a naught, which is 3. If you put a naught here, you will get n is 0, 0, lambda 1, and lambda 4. You solve it, you will get this one. And a1, you put it, you will get this a2, a3. There are multiple ways of solving this. There's also matrix methods of solving it. There's also some simple methods by just by repeatedly substituting. And by solving these, you will get your solutions. And you can simply put that back here and you'll get your answer. That is the way of solving recurrences. Any doubts till now? Yeah, let's continue. Okay, so what you had here was homogeneity. So if we don't have homogeneity, then what we do? So that's the next question. So problems like this are equations where it is not homogeneous and it is multiple order. But we consider no, there is no necessity for coefficients to be constant either. It could be variable coefficients. So this is a method of solving it. So what happens is we first consider your homogeneous part and then we consider your particular solution. So homogeneous part only, we will just see that and solve it. So you know how to solve homogeneous equations here. So you will use that and solve the homogeneous part. Then now here is the important thing. You will need to guess a particular solution. So this is where it will become difficult. So then we'll add these two. So if you consider this equation, this is your homogeneous part. And this is your non-homogeneous part. So what we do is we simply solve this homogeneous part. So if you solve the homogeneous part, you will get some expression. So this some expression will ensure that this constant is 0. So it does not solve with the constant. So that's the part of the homogeneous part. So if we simply substitute this equation and uh, write the characteristic and solve it in terms of constants, you will get this. So this is the homogeneous part solution. So if you simply put this back here, you will get an equal to an minus 1 plus 2an minus 2an minus 2. You will not have this. To get that, we will add a solution. So that is the non-homogeneous part solution that involves guessing. So this involves a very clever guesswork to get your solution. Okay, so what happens is we will guess this as your solution. The intuition of guessing why this is happening, you can get through this method. So what happens is n is a polynomial of degree 1. So we can write we can guess the polynomial of Pn plus q, which is the most general first degree polynomial that you can get. If we guess this to be a particular solution, so we are not solving it by separating homogeneous and non-homogeneous. We are solving it by separating homogeneous first, and then we are guessing a general solution. So we take this and we'll simply put it in the whole equation, not just the non-homogeneous part. We put in the whole equation. So if you put that in, so LHS will be Pn. An is simply Pn plus q. An minus 1 is P into n minus 1 plus q. An minus 2 will be P into n minus 2 plus q, but there's multiplication by 2. And there is also nth term here. So you will simplify this. So once you simplify this, you will get this. Okay. So once you're having this equation, if you observe carefully, the LHS is also first degree polynomial, RH is also first degree polynomial. There is no coefficient in the RHS, and this is valid for every n. It is not, there's no particular solution for it. To ensure that this holds for every n, we will ensure that the coefficients of both sides of n is equal. So that is minus 2 be equal to 1. And we'll ensure that the constant term is 0. So that we'll do that. So we will simply solve these two, you will get this. So now you got P and Q values. Yeah, how do we guess the solution? It will come in the next slide. So I'll explain intuition behind guessing the solution. So once you get your constants P and Q here, we will put these. So this is a particular solution. So by putting this back here, we get minus 1 by 2 into n minus 5 by 4. So that is your particular solution. You can put the particular solution. Now that you have a particular solution, you are having your homogeneous solution. You will add these two. If you add these two, you will get this term. Now again, we are given initial conditions. You will put the initial conditions and you will solve and you will find the coefficients lambda. From that you will get answer. Now why do we add it? So adding, because if you were having this solution, you will simply put this back here. The a and h term will get cancelled. We will get 0. But the a and p term will remain. That is what is ensuring that n is also included in your solution. Yes, because n is linear, we get that Pn plus q is a solution. So we'll go through a general table. So this is the art of guessing the particular solution. So you can refer this table later. I'll go through 2 or 3 rows. So if your homogeneous term is of the form n power k or any polynomial of degree k, then we will guess a general polynomial of the same degree k. Why do we do this? So what happens is you're substituting an to be some expression, right? You're substituting an to be this particular solution, right? This particular solution. So because you're substituting this, if you calculate an minus 1, you will need to put n minus 1 instead of n. So instead of n power k, if you're computing the previous terms, say n minus 1 or n minus 2, you will need to put in n minus 1 power k. So when you do n minus 1 power k, you don't only get n power k, you get all the terms from n power k minus 1, n power k minus 2. You will get all these terms, because of which we take a general polynomial of same degree k. So if you see back here, when you put this back here, we got p n minus 1, n minus 2. So because of these terms, you will also get a constant term. So if you multiply p and n minus 2, you're going to get a constant term, right? Over here, for second degree, for example, you will get the first degree term as well. So you cannot just guess n power k, you also guess n power k minus 1, n power k minus 2. So that's a general polynomial. So that's your intuition. Now, polynomial into exponential will also be, before that, we'll go to the exponential r per n. So if you're having an exponential r per n, we will guess a into r per n. So why do we do this again? So again, we will have n minus 1th term. So this is your n minus 1th term. So if you're having n minus 1th term, that will be r per n minus 1. So interestingly, r per n minus 1 is just a constant multiplied by r per n. Just a constant multiplied by r per n. So since it's just a constant multiplied by r per n, we can simply write a r per n. And the constants we can again solve for. Other examples you can see. So if you're having sum of two exponentials, it's again just superposition. If it's product of polynomial exponential, it will remain the polynomial. So for example, if you're having n power k into r power n into r power n, so this would be your uh, polynomial of degree k of n, general polynomial, into r power into a constant. Constant is generally absorbed in the polynomial, so you don't need to write your constant, and then multiplied by r power n. That will be a guess. So other examples you can have a look. Next, we'll go to the collision rule. So collision rule is what is, it's a very important rule. We'll go through it in the solution. So it basically happens when your guess of your non-homogeneous part, your guess of your particular solution, it is actually contained already in your homogeneous solution. So here, if you see, we have 2 power n minus 1 power n. Here, your guess was Pn plus Q. It is not even remotely related to these. So here, it is not an issue. We'll see an example for that. So first, let's consider this example. So this is also very similar, but here we're having 4 power n minus 1. So immediately you will see your non-homogeneous part. So once you see your non-homogeneous part, you'll be like, okay, 4 power n minus 1. So we have to guess, it is r power n form. We have to guess a into r power n, right? A is a constant into r power n. So simply for 4 power n minus 1, you will guess a into 4 power n. So once you guess a into 4 power n, you will put that back here. You will get this. You will solve for a. You will solve for a. 4 power n's will cancel, so n won't be there. Once you solve for a, you will get your particular solution. So again, the homogeneous solution, you know already how to solve. So this is a GP. So you know how to solve a GP. Constant into common ratio power n. So once you're having this and this, you will simply add them out. So this is your solution. You will use the initial conditions given, and you will find your lambda value. So that will be your final solution. I'll wait for questions. Okay, let's move on. In case of a collision rule, yeah, in case of the collision rule, what happens is, for example, you're having 2 power n. For example, you're having 2 power n in your homogeneous part of a solution, and you're also having the constant to be 2 power n. In that case, you will also guess 2 power n to be the particular solution. So now that's an issue because we are having 2 power n in both the homogeneous part and the non-homogeneous part. So there is no effect of the non-homogeneous part. In that case, we multiply by n. So that is the whole point collision rule. Yeah, so why did we guess 4 power n instead of 4 power n minus 1? That is very simple because 4 power n minus 1 is directly 4 power n by 4. So there is no point of writing 4 power n minus 1. It is just a constant multiplied by 4 power n. So that constant gets included in the constant a. So why did I add AH and AP? So that is again very simple. So because we're having two terms, the first term will become 0 when you add because this is a solution of homogeneous part. And the second term is the actual solution of the equation. So that will give you a more general form of the equation. I'll give you a reading material on collision rule in the end. I'm not having a slide on it. Okay, so next, let's move on with nonlinear. Multiply n with the so you need to multiply n with the non-homogeneous part. So for example, so let's see an example. So for example, your homogeneous part is 1 lambda into 1 power n plus 2 mu into 2 per n. So this is your homogeneous part. And your non-homogeneous part, this is, I'm talking about the correlation rule, by the way. Yes. And your non-homogeneous part is some 2 per n, again, because there is a 2 per n expression in your non-homogeneous part. So you're guessing 2 per n. So again, because you guess 2 per n, this gets included here. So to ensure that the solutions are separated, we multiply by n in the non-homogeneous part. So this solution plus some constant multiplied by this solution will be your answer. So the constant and n will be multiplied for the non-homogeneous part, not the homogeneous part. Okay, now we'll talk about non-linear ones. So non-linear recurrences are not generally solvable. We cannot, there's no direct way of solving every single non-linear one. So we'll consider only two types here. There are many non-linear ones, and especially in Olympiads and other exams, you will be asked non-linear. So in non-linear ones, you will need to observe patterns. So let's consider two types here. So the first type is this example. So over here, we are having this recurrence. So immediately by seeing this, you might have to observe that what if I divide a n minus 1? So if you divide in the numerator and denominator, you will get something like this. This comes from intuition. And you can simply reciprocate both sides. So once you do that, you'll get something like this. So if you observe carefully, why did we reciprocate? Because if we reciprocate, we can substitute bn. Yeah, so if we reciprocate, we can see bn. So once you substitute bn, so you will get bn equal to beta by alpha plus gamma by alpha into bn minus 1. So you will get this something like this. So c1 and c2 are basically constant. So you know how to solve this one, right? So we changed this to this format, and you know how to solve this. So once you find bn, you just reciprocate and you'll get an. So these require some unconventional substitution. So that's the whole point of intuition. That's where intuition comes in. So let's consider one more example. So this example, we had no constant in the numerator. So here we do. So this becomes much more complex than the previous one just because of that one constant. So again, you might have observed that whenever we are having non-homogeneity, like we are having a constant, we immediately think of substituting an equal to bn plus some constant. So some constant I'm taking to be x. We need to find what x is. So again, we do the same method. We will put your an equal to bn plus x back over here. We will simplify your numerator and denominator. So once you do that, you will get this. Yes. So once you simplify, you will get a bn equal to, once you get simplify, you will get bn equal to this expression. Now, if you observe carefully, we are having this part to be constant. This part is just constants. From here to here, it is just constants. So if I force that this constant to be 0, if we choose a particular value of x such that this is 0, then you're simply getting back this type of equation, which you know how to solve, because this part will become 0. Okay. So once you force this to be 0, so we get this one. So ax plus beta equal to x into gamma x plus delta. So once you force this and you're having two roots, x1 and x2, so you can substitute any one of those two roots. So by forcing them to be 0 and by substituting these roots as x1 and x2 in your expression, this part is forced to be 0. So you will simply get the remaining part. Now, once you're having the remaining part, there's no constant term here. So this is exactly as your same as your previous expression. You will take your reciprocal. You will set 1 by bn to be another expression, and you will solve it. This is solvable. Once you solve this, you will substitute back, and you will substitute back. You will get your expression. Or you will get bn, and once you get bn again, you will substitute back. You will get an. So that will be very complex. So the interesting note over here is that we see that this expression is simply by replacing an minus 1 as x. So if we write an equal to an minus 1, they're not really equal. But if you set that to be x, both are x, so you will get the same quadratic. So this is x is called your fixed point of the sequence. X is called fixed point. Why is it called fixed point? Because say we are having an infinite sequence which is converging in a particular value. So as n approaches infinity, you can see that n will be equal to n minus 1. So the term at nth position, n minus 1th position won't really be different. So in that case, both will be equal. So both will be equal to your constant x. So this is just an interesting note that it does not always need to converge to get the solution. So if as a infinity will be x, that is how we get this. It's called the fixed point. Okay, lastly, we are having a relationship between recurrences and DE. So recurrence will be covered by Anirudh in the next slide. So what happens is a difference operator and derivative are closely related. So difference is where you're having the change. So change between the next term and the previous term. So that is this. So as the change approaches zero, as the limit of the change approaches zero, as it tends to zero. So that is how we get a derivative. So that's how you get delta y dy. So this is the formal definition of derivative. Y of t plus h, y of t, and we are having n plus 1 and n. So that is the direct correlation. So for example, in physical scenarios like in population or bacteria growth, so the next iteration will be r multiplied by the previous iteration. That is your recurrence format. In a differential format, you can write it like this. The solution of this will be, of course, e to the power format. So that is an exponential increase, and this is increase is a geometric progression increase, exponential geometric progression. So numerical methods, which will be covered in later lectures in our summer school. So this is a numerical method. This is called forward Euler. So this will directly give you a link between the derivatives and different and the recurrences. This is called forward Euler. Forward Euler, it's a numerical method which we'll learn. Yes, so that's it. So any questions? You can ask any questions, and this is your midway attendance form. It will be open for the next 15 minutes. Yeah, forward Euler and other techniques you will cover in the upcoming lectures. It is just a method of it is just a method of linking your differential to discrete format, which is very useful in computerization. If you want to code your derivatives, this is a very unique method. There's also many more methods like RK4 and other Euler methods as well. We'll cover all this in upcoming lecture. Yes, exactly. A recurrence is a non-continuous version of differential equation, discrete. Guys, attendance form will be open for another 5-10 minutes, so fill it quick. Next, Anirudh will cover differential equations.
So, hello, I'm Anirudh. So, I'll be continuing with the session and I'll be talking on differential equations where Prajit covered recurrence. So, now, yeah, let's get on to it. And I hope all of you have marked your attendance. And if you haven't, just like scroll back, like it's a live stream, obviously. So, you can go back and mark it. The form will be open for 10 more minutes. And please mark it because it's mandatory to mark both of your attendances. So, okay, let's start off. So, what are differential equations? I mean, I think many of you will be familiar with this because I think a few of you have a basic understanding of what calculus is. So, if I want to explain differential equations in a very simple manner, it's just a function of many variables. Like, let's say I have some differential equation which is dy by dx plus 6xy is equal to 0. Now, this I can easily map it to be a function of x, y, and dy by dx. And here, y can be the independent variable or x can be the independent variable. It can be anything. So generally, this is a way of writing a differential equation. And obviously, you can write many more variables, like you can add z, you can add some d cube z by dx cube, and yeah, whatever you like. But this is the general representation of it. So if you want to talk about the different type of differential equations, generally speaking, there are two kinds. One is the ordinary differential equation, and other is the partial differential equations. So like, as you can see, there's like partial derivatives on one side and the regular ones, which you know on the other side. So when does this happen? So in any kind of equation, there's always a set of independent variables and a set of dependent variables. So now let's say you have a function y, which is equal to some 6x cubed minus sine x, let's say. Now, in this case, the dependent variable is y because it depends on the value of x, whereas x is the independent variable, and like you're expressing it in such a form that y depends on x, but x doesn't depend on y. So if we map it to here, if we have only one single independent variable, which in this case is x, and that time it's called an ordinary differential equation. So like, as you can see over here, uh, y depends only on x. So we have d square y by dx square plus 3 dy by dx plus y sine x equal to 0. So you're taking the derivative only with respect to one variable. And similarly, even in the second example, you have d square y by dx square plus 3y square dy by dx plus 5y is equal to 0. Here again, the dependent variable is y and the independent variable is x, with which you're taking the derivative. What about partial differential equations? In this case, you can see that I'm taking the derivative with respect to x and with respect to y. So what does that mean? So in this case, it means that u can be represented as a function of x and y. So as x changes, u changes, and as y changes, u also changes. So in a sense, if I have to represent it, let's say we have to draw the graph for like a function y is equal to 6x cubed minus sine x. Obviously, the graph will be 2D. But let's say you have to represent a function which is a function of two variables. Then how will the graph look like? I hope you're with me on this matter, because for one variable, the graph is 2D. So that means for two variables, the graph will be a three-dimensional, and so on. So that is how it is. So here, you're taking the partial derivative. And the partial derivative means you're keeping one of the variables constant. Like you're keeping y constant. When you're differentiating with respect to x, you're keeping y constant, and so on, vice versa. So this is an example of a partial differential equation where u is a function of x and y. Now let's look at the second example. In the second example, we have u, which is being partially differentiated with respect to x, y, and z. So what does that mean? U is a function of x, y, and z. So since this graph is in 3D and this graph is in 2D, just for the sake of mathematicians, we'll say this graph is in 4D, a four-dimensional graph. So that is about it for the basics of differential equations. Now, there are some terms related to this. I think Project might have explained in recurrences. It's pretty similar. So in this case, yeah, there's something called as the order, and there's something called as the degree. So what is the order? Like, as you can read it clearly, it's the highest order derivative present in the equation. So let's say over here itself, as you can see, d square y by dx square plus dy by dx. This is what? The second derivative, right? So second derivative means order 2. So the highest order. So that is 2. It's similar like polynomials. Just assume that d square y by dx square can be written as some y2 or something. Or instead of like confusing you with y, maybe use some other variable like f2 or something. Or f square, something like that, just for denotation. So this is order. Now what about degree? So degree is like the power of the highest order derivative, which, as you can see, it's like a polynomial itself. A polynomial of degree n has like the highest like power is x bar n or something like that. So similarly over here, the highest order derivative, mind that it should be the highest order derivative. And what is the highest order derivative over here? The second derivative. And here it's raised to the power 3. So therefore, the degree of this is 3. So I think that's clear for everybody. Yeah. Now again, just for the sake of understanding, let's again look at what order and degree are. So here, dy by dx plus 3y by 3y equal to e power x. Order is 1 and degree is 1. And over here, order is 2 because second derivative, and degree is 1 because the power is 1. And then again, order is 2, degree is 2, same like the previous one. And here, d cube y by dx cube, the order is 3 because it's the third derivative, and the degree is 4 because it's raised to the power 4. Fine. So now let's look at some examples of differential equations. And these are some standard ones which you'll find a lot in engineering and like, most problems that you occur with. I'm not saying these are the only ones. There are infinite possibilities, obviously, but these are the most standard ones. So this is a first order linear differential equation. Notice how the first order linear differential equation is similar to how Rajat had explained in like recurrences, however, without the term differential equation, obviously. So you have a function of x multiplied with y and another function of x. So it should be in this format. And, q of x could also be 0. Even p of x could be 0. It is possible, but it's not always true. But still, that would be of the correct form of a first order linear differential equation. So now the second order linear homogeneous differential equation. This is what we usually see in oscillations and other kind of stuff. And I think you might have like some familiarity with it. And the basis of it is that you have a second derivative involved. That is the only thing that's different from the first order linear differential equation. And this will be an important part in our lecture. We'll learn how to solve such later. And the general linear differential equation in terms of power series. So what is a power series? We will be seeing on that later. But yeah, just assume that you can write AK as a polynomial. Like you can write the differential equation in terms of a polynomial of a function. This is similar to what Rajat explained when writing the characteristic polynomial for a given, uh, general linear like recurrence relation. And finally, continuing from here, second order linear non-homogeneous equation. Why is this non-homogeneous? That's because of this term over here, which is not related to y. And hence, it acts like a constant term. You can think of it as that way. So yeah, that's why it's a non-homogeneous linear differential equation. Okay, I hope everybody is clear with this. This is just the basics. Fine. So now let's look at a basic standard form, y dash plus px, y is equal to q of x. What does this automatically translate to? dy by dx plus p of x times y is equal to q of x. Now, there's a trick for solving such kind of questions. You find something called as the integrating factor. And what is the integrating factor? You take e power integral p of x dx. And some people might ask, is this definite integration or indefinite? It's indefinite, I'll tell you, but there's no constant term. And why is there no constant term? Well, there can be a constant term, but I'll show you how this doesn't matter. So you have e power integral p of x dx. And let's say there is a constant term plus c. So this will, I can just write this as e power integral p of x dx times some e power c. E power c is some new constant a. So I can write it as a into e power p of x dx. So now the way to solve this is after dx multiplied by a, I multiply both sides because the constant a just gets cancelled out as function of x. So as you can clearly see, if we find out, we get like what? We get this exact, and hence
Okay, so I hope like we're sorry for the difficulty. Like the tech, we had some issue, so now we sorted it, and I hope you all remember where we left off. So we are trying to find a solution for this standard form, which is a first order linear differential equation. So what we found is that we have an integrating factor, which is e power integral p of x dx. And do note that uh, we need to always have the differential equation in this form if we want to find the solution like this. And what I mean by that is the coefficient of dy by dx should be 1. And that's the main part of it. And it should be a linear form, obviously. That's the only thing. So what we do is multiply this integrating factor over here. And after doing that, we get the RHS term, which looks a bit weird now. And we get an LHS term. But if you do notice that the LHS term beautifully can be written as the derivative of this term, y e power integral p of x dx. Just try differentiating this function once and try writing it. You might understand what's going on. So we get it like this. I hope that's clear. So fine. Then what else? After this, we integrate both sides because that's what we do. We always integrate. And after integrating both sides, you get this to like the integral of a derivative is the function itself, which is y e power integral p of x dx. And on the right side, we get some complex integral, which obviously depends on the way the question is. And then there's a constant term. So let's look at a decent example on this question. So I hope everybody is clear up till this point. Okay, if everybody is clear, then we can like just look at a question. So let's say you have some 2 dy by dx plus some I don't know x times y is equal to x cubed. Let's say. Then how do we try solving this? So first of all, let's find the integration factor. Integrating factor. So this is p of x. So what is the integrating factor? E power integral x times dx. But is this correct? This is not actually correct because we need the differential equation to be in the form of dy by dx, like where the coefficient of dy by dx is 1. But here, what's the coefficient? It's 2, right? So what we need to do is just divide both sides by 2, and we get um, x by 2 x cubed by 2. Okay, so now this will be x by 2. So integrating this, we get our integrating factor to be e power x squared. So we need to multiply both sides by e power x squared, and then we can just solve the equation. I hope that's clear. And this might not even be solvable. You never know. Like this integral might not be solvable. Like finally, q of x will be x cubed by 2, and this will be e power x squared dx. But do you think this is solvable? Well, it actually is, because if we write x squared as some t, then dx 2x dx will be equal to some dt. This is a substitution that we can use to like solve this. I hope everybody is clear with this. Oh yeah, my bad. This should be x squared by 4. Sorry about that. Okay. I hope this is clear for everyone. Okay, now looking at the previous thing that we had discussed, general linear differential equation, the power series representation. Let's look at it once more. The power series representation. So mathematicians thought, is it possible to write a given function as a sum, like sum of infinite things, or just a sum of some random thing? So it in fact turns out to be true that you can write a function as a sum of things. And what is the easiest way to like write a function? What is the easiest type of function that you can think of? The easiest type of function is obviously a polynomial. So obviously we chose to write a polynomial representation of a function, right? So that is what we try to do. So y of x is a function of x. So we write a polynomial in terms of x, and this goes on till infinite terms, mind you. That is a speciality of the power series representation. So many of you might have heard of the Taylor expansion. So what is the Taylor expansion? So Taylor expansion series is just a function where about a point A, you find all its derivatives and then compute it, and then you write an expansion in this format. And with writing by writing the Taylor series expansion, you can find out a polynomial for any given function. Like just find out note that a is a constant. So this is just a number. All these things, f of a, f dash a, f double dash a, they're just numbers. So in the end, what you get is an infinite polynomial. Now you all might be wondering, uh, is this even true? So the thing is, this is only true when some conditions are achieved. So for example, uh, the power series exists only if the function is continuous. And this is very true because obviously you need the function to be continuous. Like let's say you want to find out some y of x naught. And we know that polynomials are always continuous, right? Every given polynomial is continuous. So if you want to write a given function in terms of a polynomial, then y of some x naught plus should be equal to some y of x naught minus for us to write a polynomial expansion of that function. And as somebody asked in the chat, just to approximate things, we are finding power series. If you write it for infinite terms, and given that all these properties are satisfied, it won't be an approximation, it'll be the exact value. And you can write it for approximating things also if you expand it up to finite terms. And yeah, as somebody mentioned, there's analytic functions where we check whether the limit exists at that point or not, which I'll be covering later. So power series should be continuous. That is one thing. And the second thing is for the existence of power series that like the series must be convergent. So just to give you an idea of convergent series, uh, let's say you have a series which is, let's say take some series which is 1 plus 1 by 2 plus 1 by 4 and so on. And what is this equal to? Obviously, we all know that after infinite terms, this gets equal to 2, right? So this is an example of a convergent series. Like no matter how many terms I add, it always converges exactly at 2, provided that I go till infinite terms. Now let's look at another series. Let's say you have a series where if uh, for every even term is 1 and every odd term is -1. So summating this, what do we get? 1, -1, +1, -1, +1, -1. So this is oscillatory in nature, if you can see. So after infinite terms, if you ask, like, if you're asked to tell the value of this summation, will it be 1 or will it be 0? In fact, we can't conclude this because this series is not convergent at all because it's not going to a finite value. Like, depending on what terms I'm taking, the value of this changes. So this is not a convergent series. Another example would be something like 1 plus 2 plus 3 plus 4, which is also not a convergent series, and this blows up to infinity. And another example would be 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, and so on. An interesting fact about this series is that the terms converge. As you can see, every successive term is lesser than the previous term, and the final term tends to 0. So the like values in the series converge to 0, like finally at n equal to infinity. However, the summation doesn't converge to 0, and this in fact blows up to infinity. So this is a very interesting thing which you must note, that the terms itself might converge to 0, but that doesn't mean that the sum converges to 0. Okay, I hope this is clear. I'll move on to the next one. Okay, so how to check if a series is convergent? There are many tests that you can use for a series to be convergent, like uh, the sum of the nth term minus the sum of the n minus 1th term. This is a thing that you will learn in like calculus further on. So if this is lesser than some finite value L and n tends to infinity, then we can see that the series is convergent. That is one thing. And another thing could be the ratio test. Like, let's say you have this Sn means the sum of terms. Another thing is the ratio test where let's say you have the anth term and let's say you have the an minus 1th term. If this is less than 1, then the series is convergent. And if this is greater than 1, then the series is divergent. And if it's equal to 1, then we cannot conclude what happens. A nice example of this would be, uh, let's say you take the previous series, 1, 1 by 2, 1 by 3, 1 by 4. So the nth term is 1 by n, and the n minus 1th term is 1 by n minus 1. Now you might say this is less than 1, but the limit approaches 1. So that means it is equal to 1. So that means at 1, this is inconclusive. We can't tell whether it diverges or converges. We will have to check whether it's like, diverging or converging by just summating it. And the radius of convergence differ, like over here, let's say we take at A, it refers to the maximum value up till which like the series is convergent, which I'll explain right now. Just give me a minute. So let's look at some examples over here. So this is e power x. So e power x, if we use the Taylor expansion, which I mentioned before, you will get this to be the exact series if we take the Taylor expansion for a equal to 0. So we get 1 plus x squared by 2 plus x cube x squared by x cube by 3 factorial and so on. How can we verify this? Well, this must be equal to e power x and this is e power x. And we know that d of e power x by by d of x is equal to e power x. Simple test. So with this, let's try doing it. Let's differentiate this. You get 0 plus 1 plus 2x by 2 factorial plus 3x by 3 factorial and so on, which again is equal to 1 plus x, 3x square, my bad, plus x square by 2 factorial and so on, which is again equal to e power x. Similarly, over here we have sin x and we have cos x also. So how do we conclude? This is also done by Taylor expansion, which by taking a equal to 0, right? So sin x is equal to this and cos x is equal to this. A good way to, prove this would be trying to differentiate sin x. And if we differentiate sin x, we must get cos x. So let's differentiate this. Differentiation of x is 1. Differentiation of 3x cubed by 3 factorial is x squared by 2 factorial. And x power 5 by 5 factorial. Now, somebody asked, these are valid only when x tends to 0, right? This is actually a wrong statement. The finite number of terms approximation is true when x tends to 0. However, these series, they're valid for all x. And it is true. If we try to calculate it, we get that these series, regardless of what a you choose, like here we took the Taylor expansion at x equal to a. Let's say we take Taylor expansion at x equal to some finite x, some n. It'll still be true because here when we try to find the radius of curvature and what is the radius of convergence? For the radius of convergence, you'll always get it to be infinity. Like let's say I want to draw a graph and this is the point where the limit x, this is the point where this is the point, like let's say this is x equal to a and let's say this is some a plus r and this is some a minus r. So the region in this region is the region of convergence where it exists. And there's a subtle way to find this out by like taking limits of like n tending to infinity. And like with this, you will get that the radius of convergence is like infinity for these three series. So that's why this exists for all x. I hope that's clear. And somebody asked that definition of convergence, and by this definition of convergence and divergence, shouldn't 1 by n series be convergent? Well, like I mentioned over here, we are doing there's a ratio test, right? An by a of n minus 1. When you're applying it for n equal to infinity, uh, the nth term is 1 by n, and the n minus 1th term is 1 by n minus 1. You might be, you might be feeling that this is obviously less than 1, but you're taking n equal to infinity. Keep that into mind. So we have to take the limit. So this is not less than 1. This is in fact equal to 1. And for n minus 1 by n equal to 1, this series, it's inconclusive whether it converges or diverges. So we can't give a proper explanation about it. I hope that's clear. So let's look at the last example, which is 1 by 1 minus x is equal to sigma x of n equal to 1 plus x squared plus x cubed. So this is a special case because here it's not true for all x. So why is this happening? So let's say I put x is equal to some 5. All right. Let's say I plug this here and let's say I plug this here. Here I get this is equal to -1/4. And here what do I get? 1 plus 5 plus 25 plus 125 and so on. So we clearly know that this is a negative number and this is a positive number. And this doesn't exist. So what does that mean? That means that there's a radius of convergence around which this value cannot like further exist. The radius of convergence is like used in real analysis, which is another topic of mathematics, which we will not be discussing today because that again can be explained in much detail and it'll take time to understand. But just understand it as the point where the limit converges. Okay. So here, the radius of convergence, as we all know by geometric progression formula and all that, is mod x less than 1, right? So that means x should be lesser than 1 and greater than -1 for this to exist. So this is the region of convergence. I hope that's clear. But for all these cases, there is no region of convergence. It exists for all x. Okay, I hope that's clear. So coming back to our initial question, why do we need it for a differential equation? Let's take a very simple example. Let's say we have dy by dx is equal to y. Now we know we can solve this naturally by taking y to this side, bringing x to this side. But let's use another trick and another method to solve this. Uh, Take this, and let's say we have an initial condition y of 0 is equal to y naught. Now assume that a power series solution exists. Take an assumption, and let's see how it works out. So you have y of x is equal to a naught plus a1x, where ai is element of R. Remember that. For this case, we'll take ai is equal element of R. So we have a naught plus a1x plus a2x squared plus a3x cube and so on. Now take y dash x when you differentiate term by term. You get this, right? So you get a general term n times an multiplied by x power n minus 1. However, do note one thing that the summation is going from 1 to infinity this time because we can't have a negative power of x, right? So we need a base coefficient. So that is why we do this. So now equate these two. Equate y of x and equate y dash of x. Y dash of x is equal to y of x. What do you get? Think about it. You get a1 equal to a naught, 2a2 equal to a1, 3a3 equal to a3 equal to yeah a2. So what is the general type of like answer that you're getting? N plus 1 times an plus 1 is equal to an, and an plus 1 equal to an by n plus 1. I hope you're all familiar with this kind of equation which Prajit had covered in his uh, recurrence series. So this is very simple to solve. Why? Because we have an initial condition where y of 0 is equal to y naught. And what is y naught? Plug in x equal to 0 over here. All these terms will cancel out. So y of 0 is equal to a naught. So we get a1 equal to a naught, 2a2 equal to a1, 3a3 equal to a2, and so on. So finally, what do we get? We get y equal to y naught, 1 plus x squared by 2 factorial plus x cubed by 3 factorial, and so on. And finally, we get y naught e power x. I hope that's clear. So let's say we try to back substitute it. Y naught e power x should be equal to the derivative of it, which is true. So we get this. And that means it is a proper solution for that. Okay, I hope this is clear for everyone. Now let's look at an interesting topic, which is called as the Laplace transform. Hmm. You might be wondering, what even is this? Uh, we will use this further to solve differential equations. So let's look at it now. So essentially what a Laplace transform is it's an integral. Let's say you have a function f of t. It depends on some variable t, and you're integrating it with respect to e power minus ft. So do note for this integral, s is equal to constant because the integration parameter is t. So with respect to dt, s effectively acts as a constant. And since your in like limits of t tend from infinity to minus infinity, that means it's the final answer should be independent of t and should only be a function of s. So that is a function of s called f of s. I'm just taking it that way. And another important aspect, s is the element of complex numbers. Obviously, all real numbers are a subset of complex numbers. So s can be equal to 3 plus 4i, where I is equal to root of minus 1, or s can be simply equal to 3i, or s can be equal to 4, and whatnot, whatever is possible. So this is one thing. Do note that when we apply a Laplace transform, which is this Laplace transform of a function of f of t, results in a function of a different variable. So the variable is changing from t to s, right? I hope that's clear. So that is what's happening. If anybody has any doubts, just ask it now. Okay, I hope that's clear. So just remember this, we will be using this further. So now let's look at some weird functions, as I'd like to call it. So first of all, one is the unit step. So the unit step is essentially 0 for t less than 0 and 1 for t greater than or equal to 0. Okay, I'll explain this again, but first let's look at these functions. So for unit step, it's just a function that I'm defining, uh, where it's less than 0 for less than 0 it's 0, and for greater than 0 it's 1. Do notice the discontinuity at t equal to 1. We will talk about it, but it's not a necessary implication and it doesn't really matter much. And the second function is the most interesting function in my opinion, which is the Dirac delta. So what is Dirac delta? So Dirac delta essentially is not even a real function, if I have to say. So at t equal to 0, uh, you have the Dirac delta function to be equal to infinity. And at t equal to t not equal to 0, the function like is 0. So I can just write it as like this graph and some point way beyond whatever we can see to be the value of the Dirac delta, and everywhere else it's 0. So some of you might ask, why is this even a thing? Why do we even need something like a Dirac delta? Like t equal to 0, it's infinity, and t not equal to 0, it's 0. So hmm, let's say you have, I think many of you might know about impulse, like that's the one that's in physics. Uh, so what exactly is impulse? Impulse is a sudden change in momentum because of like a very like a strong force applied for a very short interval, right? So I can represent impulse as something like this, right? And this lasting for some time delta t, right? And it goes to a very high value. Now keep increasing the length and keep decreasing the time interval delta t. So what will happen if you keep decreasing the time interval delta t? Make delta t tend to 0 and this height h tend to infinity. So you might get cases where in computation, you might get sudden bursts. Like, let's say when you're starting a car or something like that, you'll have to suddenly apply some thrust, like the engine does that. So that is easily visualized by a Dirac delta because compared to the other like forces or something like that, it's very large in magnitude. So it's a very easy way to visualize it in this way. But do note that Dirac delta is not a real function. And coming back to the explanation of Laplace transform, the Laplace transform is simply an integral, which is an integral of a function f of t. This is just a random function that you have. This could be some uh, t cube sine t, something like that, and which is multiplied by e power minus st dt. And then the limit tends from infinity to minus infinity. And yeah, where effectively acts as a constant, right? So that is it, I think. And do note the variable is changing from t to s. So it's just a way of transforming the variable. And as somebody had asked, is it similar to Fourier transform? The one difference you can see from Fourier transform, if anybody knows what a Fourier transform is that in Fourier transform, we deal with uh, real values, and we deal with like only imaginary values. My bad. We don't deal with complex values. And yes, it is used for analyzing AC circuits. For now, if you're not understanding, just remember that the Fourier transform is simply just this integral. All right. You'll get to understand how we deal with it in like the further slides. So I hope you remember what the Fourier transform is, the Laplace transform is. Okay, you don't have to know what a Fourier transform is. Don't worry on that. Right. Just remember there's a Laplace transform. I just mentioned Fourier transform for those who understood what a Fourier transform is. You don't have to know what a Fourier transform is right now. Just think about the Laplace transform that I mentioned here. Right. Okay. Just remember this. Yeah, that is one way to visualize it. But right now we don't have to talk about the Fourier transform. There's no need for you to know it. So let's take a function f of t equal to u of t, the first weird function that I had mentioned, the unit step over here, right? So let's take the Laplace transform of u of t. So let's integrate from infinity to minus infinity u of t. Now we know that u of t is 0 for t less than 0. So obviously we can directly write it from 0 to infinity, e power minus st dt. This is a very standard integral. S is equal to constant for the sake of the integral. Remember, only for the sake of the integral. And then we get this. Now, this is the most interesting part of it here. Now we need to plug in values. So e power minus st by s at t equal to infinity. What will this become? E power minus s into infinity. You can't obviously write multiplying by infinity, but just for the sake of understanding, let me write it. E power minus s into infinity. Now, does this value exist if uh, s is less than 0? For this value to exist, like we know that e power minus infinity is 0 and e power infinity is infinity, right? So we want this value to be like finite. We don't want it to blow up. So that means we necessarily want s to be greater than 0. And okay, my bad when I tell this, when I said s to be greater than 0 or s to be less than 0. When I'm talking about greater than 0 or less than 0, I mean the real part of s. For now, assume that s is real, just to not overcomplicate things. But just for the common sake of understanding, I'll say real part of s should be greater than 0. I hope that's I hope that's understood why we are taking a real part of s greater than 0. Because if real part of s is less than 0, then this blows up. And somebody is asking, what if s is complex? S can be complex. Let's say you have s is equal to 3i plus 4, let's say. But this 3i, I think many of you might know Euler's form of writing complex numbers. Uh, Anybody knows? So e power it is what? Cos t plus I sin t. So what does that mean? At any like given t, this is a finite value, right? Like the modulus of e power it is always less than 1, lesser than or equal to 1, right? So this is an oscillatory component. This does not affect what the magnitude of this goes to. So no matter what time you take, so then it's always like, convergent. You can say it's convergent for now, right? So that's why the imaginary component doesn't matter. Only the real component matters because let's say you have e power minus 4t. At t equal to infinity, this tends to 0, right? So that is why we're taking real part of s greater than 0. I hope that's understood. And finally, you get 1 by s as the answer. I hope that's clear for everyone. And the ROC just refers to the region of convergence, the point where, and this is somewhat different from the previous one where we were discussing for analytic functions like the Taylor series. But the region of convergence here is basically real part of s greater than 0 if you want to plot a graph. Now, similarly, let's take the next example. F of t is equal to minus u of minus t. And let's say we integrate this. Again, same procedure. This is, but since this is the inverse function, I hope you all know how to draw the graph of negation. Like if u of t is greater, like equal to 1 for greater than 0, then u of minus t will be equal to 1 for less than 0. So we get this, and then we get this. Now again, the similar manner of simplification if we use over here, we need e power minus st, s into minus infinity to tend to 0. So what does that mean? S should be real part of s should be less than 0 in this case. I hope that's clear. This is just a counter example. This is just a negation of this. This I'm just showing how two different functions can exist like this. Okay. But do note one very interesting thing. Both of these two functions are different, but both of these have the same Laplace transform, right? But what is the only differentiating factor? The region of convergence. Here it's s greater than 0. Here it's s less than 0. I hope that's understood now. Now, similarly, you can add another function, e power minus at u of t, and you get minus e minus s plus a t infinity to 0, 1 by s plus a. So just think about this for a while, these two, like example 3 and example 4, and ask me if you have any doubts. Because this is similar to the first two examples. It's just integration and like looking at where the integral doesn't blow up. I'll wait for a minute. Okay, I think everybody is clear with this. So do remember this. Do remember one major thing, by the way. Like a single function can have multiple, like different functions can have the same Laplace transform, but the region of convergence is different. So that is one, the region of convergence and the Laplace transform. Both of the other thing, both of these things are the ones which need to be specified for a given function. So I hope that's clear. And yeah, somebody asking, can we use Dirac delta function over here? Absolutely, you can use a Dirac delta function. Like you can find a Laplace transform of Dirac delta, which it will fit in here. try doing it once. It's like, try it as an exercise. So what do we do with the Laplace transform? Just wait for a bit. So some interesting facts about the Laplace transform. Um, Laplace transform change the independent variable from operation from t to s. So that we had seen clearly, like the function itself changes. So they exist only if the Laplace transform interface converges. So what should exist? The region of convergence. And that there are different types of Laplace transform. One is the bilateral one, and one is the unilateral one. So the one that we saw over here, this is the bilateral Laplace transform. And what do I mean by bilateral? The limit tends from minus infinity to infinity. That means it's a bilateral Laplace transform or just the regular Laplace transform. So what about something else? Like, let's say this case. This is called as the unilateral Laplace transform. And the reason for this is being uh, the limit tends from 0 minus to infinity, not from minus infinity to infinity. That's the only difference. But this is the one that we will generally use to solve real life problems. And I hope, like, you guys just be patient for a bit. It might seem that, it's very, out of place, like nothing related to what you're doing. But I'll show you in a minute that how it's related. And somebody asked me why it has to be from 0 minus to infinity. So that is a way of defining it. And the reason we are doing 0 minus is to, like, assure uh, continuity at 0, continuity and differentiability at 0. You can write it as 0 to infinity also. It doesn't matter. But usually it's a better notion to write 0 minus because that assures continuity at 0. Because some functions, like, it might have a value at 0, like y of 0 is equal to y naught or something. This is defined only when, like, 0 is continuous, right? So that is why we take 0 minus. It's just a notation. Also, we are talking about the Dirac delta, right? So the Dirac delta can be represented like this. Like, it's a function at 0, it goes to infinity, and at all other points it's 0. And similarly, this is a shifted Dirac delta. So the shifted Dirac delta is just add x equal to x naught. This function blows to infinity. And the most interesting fact is this. The integral of Dirac delta from 0 to infinity is 1. Again, if you want to visualize this, just imagine it like a triangle, and this height is some h, like delta h, and this height is some, actually, wait, uh, yeah, this height is some 1 by delta h, and this is some delta h. So delta h should tend to 0, and 1 by delta h should tend to infinity. This is the principal way of defining how we write a Dirac delta. So the product is what? 1. This is how we define it, and we get the integral to be this. It is just by definition, and obviously the Dirac delta is not even a real function because we can't have a function that goes for, like, that goes up to infinity. We're just doing it for, you know, analytic and computational purposes. Okay, people are asking how can the integral be 1? Like, just like I told, the basic definition of how a Dirac delta is you have a triangle, visualize it like the triangle. Yeah, it's like saying that infinity into 0 is 1. So like I said, it's not a real function. You just have to accept the fact that it's like this. It's the way we have defined it. All right. We've defined that limit to be 1. This is some delta t, and this is some 1 by delta t. I mean, here obviously by, like, you get it to be 1 by 2. But let's say you take this 2 delta t. Fine. This is 2 delta t and this is 1 by delta t. And that is how it is. So I hope that's clear for now. Just do remember the unilateral Laplace transform. We'll be using this in a bit. And yeah, we can uniquely determine an initial function if we know the transform and the ROC. Mind you, we need to know both. If we know only the Laplace transform, then we can't uniquely determine it. There can be multiple functions satisfying it. And yeah, this should be 2 delta h and this is 2 delta t. My bad on that. Okay. Now, what we are actually focusing on, differential equations. So let's say we take Laplace transform for derivatives. How does that work? So let us take, okay, by Laplace transform here, I mean unilateral Laplace transform because that's what we will be using for this kind of stuff. So what is the unilateral Laplace transform? This. So let's get on to it. So let's say you have some y of t. So let's say, okay, I've defined it here. So y of s is the Laplace transform of y of t. Let's take another function x of s, and I define that as the Laplace transform of y dash of t, right? So what will that be? Integral 0 minus to infinity y dash of t e power minus st dt, right? So this is x of s. Now let's use some basic integration techniques. So I hope all of you know how to do integration by parts. So take this as like do the UV method, and what do we get? We get this to be equal to, 1 second. This can be written as d of y of t. So I can write this as y of t times e power minus st limit infinity to 0 minus y of t times s times e power minus st dt, right? 0 minus to infinity. Okay, so let's try plugging in some values. Here again, at 0 minus, what do we get? I think we get minus y of 0. And what do we get at infinity? Like we mentioned in the ROC part, like when we were discussing the examples, we need this not to blow up. We want the Laplace transform to exist. So we need s to be greater than 0. Real part of s to be greater than 0. All right. So real part of s is greater than 0. So we get just minus y of 0 because at infinity, this limit goes to 0. Now, what about this part? Here, as I mentioned earlier, s effectively is a constant in this integral. All right. So I can just take the s out. And if I just take the s out, it's just integral y of t e power minus st. So it's just the Laplace transform of, okay, my bad. Yeah, this should be plus. And yeah, so it's just the Laplace transform of what? Y of t, right? So I can just write it as y times y of s. So the final sum will be s times y of s minus y of 0, which is exactly what we got over here. I hope this is clear for now. We get this by using integration by parts. Now, let's say you want to find Laplace transform of y dash of t. Again, like Prajit covered, we'll use recurrence relations to get it. So Laplace transform of y dash of t can be written as s times x of s minus y dash of 0. Why y dash of 0? because here our function in consideration is y dash, L of y dash of t. Like, because our initial function is y dash of t. Like, for y dash of t, we get y of 0. So for y double dash of t, we should get y dash of 0. And what is x of s? We know that this is x of s. Let's plug that in. So we get s square times y of s minus s times y of 0 minus y dash of 0. I hope this is clear for everyone. Similarly, we can find for other derivatives of y as well, and we can get a good idea of what is going on. Okay, so now coming back to the major question, what all of you are asking, where do we use this? So this is used in solving differential equations, like we'll see over here. Now, here comes the fun part. So let's say you have a differential equation y double dash plus 3y dash plus 2y is equal to 0. And you have initial conditions where y of 0 is equal to y naught, y dash of 0 is equal to y1. Now, why do you need these initial conditions? Well, let's just say for like for an nth order differential equation, you need n initial conditions. So for a second order differential equation, you need 2 initial conditions. All right. So let us do some interesting thing. Let's take the Laplace transform on both sides and assume that the Laplace transform of y of t is equal to y of s. Okay. Now, after doing this, we took the Laplace transform on both sides. So y double dash has a Laplace transform of this. 3y dash has this Laplace transform, and y has a Laplace transform y. And Laplace transform of 0 is just 0. I hope that's clear. Now let's collect all the y terms on one side and the other terms on the other side. All right. Now, yeah. So what is y of s? Y of s can be written as s times y naught plus y1 plus 3y naught divided by s plus 1 by s plus 2. Now, this also can be written as a by s plus 1 plus b by s plus 2. I hope all of you are like, good with partial fractions. So it's the way of splitting, two terms by writing it like this. So if we multiply this, like if we want to express it in this form, because I hope you all remember over here, we have a Laplace transform invertible in the form of 1 by s plus a. So we know what the inverse Laplace transform of this is. So the inverse Laplace transform of 1 by s plus a is either this or this. So we need to represent it in that form. So that is why I'm writing it like this. All right. So a by s plus 1 plus b by s plus 2. Now by simple, solving two equations in two variables, like you always like it's really simple. Just do it and you will get this. I hope everybody is following up till here. So now what do? We write it in the form like this: 2y naught plus y1 by s plus 1 whatever. Lot of complicated looking stuff. So let's say we write it like this, and then what? Uh, Before we complicate stuff, a by s plus 1. If I want to take the inverse Laplace transform of that, can I write it as some like can I write the inverse Laplace transform of this as some a a1, which is a different constant, times e power minus t? Can I write it like this? Like if you see over here, 1 by s plus a always has a Laplace transform of u of t times uh, e power minus at, or u of minus t times e power minus at. Right. So this always has a Laplace transform of this way. And since u of t is always equal to 1, and u of minus, like u of t is always equal to 1 and minus u of minus t is equal to minus 1 or 0, I can write it in the form as some like a times e power minus at. Can I always say that 1 by s plus a is always in the form of a e power minus at? I can always say this, right? Because regardless of u of t, it'll always be a constant. It'll be 1, right? So a e power minus at is the standard form of 1 by s plus a when we are trying to write the like inverse Laplace transform. And this a constant can be anything. And it varies based on the ROC. So if s is greater than 0, I mean s is real part of s is greater than minus a, then a will be equal to u of t. And let's say real part of s is less than minus a, then what do we get? We get a to be equal to minus u of minus t. So I'm treating this as some constant a. That's all. I hope that's clear. So that is what I'm doing. I'm writing this as some new constant a1 times e power minus t, and this as some new constant b1 times e power minus 2t, because here it's 2 and here it's 1. Here a is equal to minus 1 and here a is equal to minus 2. I hope everybody is understanding that. All right. So this is what we get. So basically we had y of s. Uh, Let me erase a few stuff. Y of s, we had y of s is equal to a by s plus 1 plus b by s plus 2. Now clearly I can write that without even understanding what the ROC is. I can clearly write that y of t, if I take the inverse Laplace transform on both sides, I can clearly write that this is equal to some a1 times e power minus t plus b1 times e power minus 2t. All right. I hope this is clear. Now, how do we find what a1 and b1 are? You have two unknowns and you have two variables. You have two knowns and you have two variables. So you can easily solve for this. I hope everybody is clear up to this aspect. Now, previously I had mentioned about ROC, but here nothing is given about ROC. But what if it was given? What if ROC was given? Then let's look at this. If the ROC was given, then there'll be three cases, because here we have two things, right? We have minus 1, minus 2. So let's say this is region 1. Let's say this is region 2. And let's say this is region 3. Now, based on what we had understood before, in these three regions, everything will be like in this. I'm so stupid. I wrote minus 2 and minus 1 over there. My bad. Yeah. So minus 2, minus 1 here. So in these three regions, we'll have different ROCs. Like your ROC could be this region or this region and this region. So based on that, you get different differential equations. And as you can see, all of these are in the form of a e power minus t plus b e power minus 2t. All of these are in this form. And based on your initial conditions, you'll always get the answer in such a fashion. And if you want to look at these ROCs, just remember like this. For a given, like treat them as independent functions, like treat 1 by s plus a and the 1 by s plus b thing as independent functions and check for what the ROC is determining. Like for example, in this case, when real part of s is less than minus 2, that means real part of s is less than minus 1 as well. So both of these functions will follow the similar pattern, which will be u of minus t, and that is there here. And let's say in the second ROC, which is this region, we have real part of s less than minus 2 and real part of s less than minus 1. So in this case, we have the first one, which is like the first for -1, it's on the left hand side. So it'll be minus t. But for the -2 one, it's on the right hand side, so it'll be u of t. And what about the other one? Other one, we have real part of s greater than -1, so it's greater than both. So that means both of them will have u of t. And like somebody was mentioning in chat, the equation method is much faster. But that again, you're getting with the Laplace transform itself. And here, just because ROC isn't given, so that is why you're using the equation method. But if the ROC was given, this is how you would be solving it. So I hope this is clear. You can solve it in both ways, but for both of these ways, Laplace transform is a very easy method. Here it might seem a little bit, overwhelming, but soon if you like practice a bit, it'll become very handy. Yeah, so you can find your initial function y of t based on this. I hope that's clear for all. Okay. So now let's take some facts about solutions. Okay, the equation method is just, taking partial fractions right over here and assuming that a by s plus 1 has an inverse Laplace transform a1 times e power minus t, which it actually does. And b by s plus 2 has an inverse Laplace transform b1 times e power minus 2t. We know that it's like some constant because u of t is always a constant in a given interval, right? So in that given interval, you're taking a constant and then you're solving it. Because obviously, when you're solving real-time differential equations, it'll always be in a given interval. So based on that interval, your constants will change. So this is the method of solving it if you don't want to look at the ROC. And this is if you're using the ROC. Yeah, so now looking at some facts about solutions. Uh, as Prajit mentioned earlier, there are homogeneous solutions and non-homogeneous solutions. And I think I covered it too, that this is a non-homogeneous differential equation because of the term e power x. So the corresponding homogeneous equation is y double dash minus 5y dash plus 6y is equal to 0 because remove the constant, obviously. That is the way. So let us say that a solution for this is yh. All right. So let's say I have another, variable alpha times yh, where alpha is element of R. Let's take it to be element of R for now. So if yh satisfies this equation, it means that yh double dash minus 5 yh dash plus 6 yh is equal to 0. That is what it means if it's a solution. Now, what if I plug in alpha yh in this equation? I get alpha yh double dash minus 5 alpha yh dash plus 6 alpha yh is equal to 0. So what does this mean? I'm getting alpha yh dash minus 5 yh dash plus 6 yh is equal to 0. And this, we know it tends to 0. So that means alpha yh is also a solution of 0. Solution of this, a homogeneous solution, right? So if any yh satisfies this equation, that means even an alpha yh satisfies this equation. I hope that's clear. Now let's say we have a particular solution for this. All right. And let's say yp is a particular solution. So this is what it means when it's a particular solution. All right. So now people were asking, what can you explain particular solutions and homogeneous solutions again? Homogeneous solution is a solution for this, and a particular solution is a solution for this, which is this equation. Now, why do we write the general solution to me in terms of y equal to yh plus yp? The reason is, let's say you take this equation and you plug in a value yh plus yp. Let us try doing that. You get yh double dash plus yp double dash minus 5 yh dash minus 5 yp dash plus 6 yh plus 6yp is equal to e power x. Right. Now, can I write this as uh, yh double dash minus 5 yh dash plus 6yh plus yp double dash minus 5yp dash plus 6yp is equal to 0, equal to e power x, my bad. So we know that this is equal to 0. So this cancels out. And we know that this is also equal because the particular solution satisfies this. So what does that mean? That means the sum of a particular solution and the homogeneous solution also satisfies this. So what does that mean? Actually, the general form is some alpha yh plus yp, where alpha can be 0 also. So this is a general form of this kind of solution. I hope that's clear. Why do we include yh in the first place? Because see, for if you want a general form of the solution, if you know that if let's say you know yp is satisfying it, but let's say you know some other solution which is yp plus some yh is also satisfying it. If this is also satisfying it, then isn't this a more general solution? Like yp plus yh. And if we know that yh is satisfying it, that means some alpha yh is also be satisfying it. So this is a much better, way of telling it because it's a much more general solution. So that is why we include the homogeneous solution. It's like saying, let's say you're doing an integration, and for integration, you get some integration constant based on what the interval is. You can treat the yh to be, the value of the integral and yp to be equal to the integration constant. I think that's a much better way to understand this. All right. You'll always have to include the integral. Just at some values of like the function, you get the constant, but you'll have to include the integral, right? So you can think of it as that way. Okay, I hope it's clear for everyone. So I hope there. I hope so. Do you have any questions? If nobody has any questions, then I think we're done. No, in this case, yp is more suited to be the constant because it's appearing because of this term, which is like a constant term. You can say that. Okay. Yeah, we solve this DE using Laplace transform itself. Yeah, like I mentioned, it's a good exercise to solve this differential equation using the Laplace transform. Try it. The only difference over here is that there's a constant, there's a constant term. Like this e power x is there. So here your y is a function of x. So your integral will be respect to x. So over here, you'll have an additional term over here, which is you'll have to take the Laplace transform of e power x also. That's the only thing. Are there any other questions? How do we find yp? You find yp by using the Laplace transform. I'm not doing it for you because I don't want to do everything. Just try it on your own. Like as we solve for the YH over here, as we solve the solution over here, it's the exact same way of doing it. But just that you'll have to include this e power x into consideration. So okay, how do we know that all functions will have a inverse Laplace transform? Well, sometimes all of them won't have it. That is a constraint that is there. But most of the things that you see will have it. Like in a general second order linear differential equation, which is there in most of your engineering cases, you can find a Laplace transform. Some of them might not be integrable, though. That's the only kind of trouble that you might face. And uh, if there are no questions, then I think we can end it. Okay, then we'll end the session.
Thank you all.